Hi everyone, Mrs. Jackson here. A quick video on how to simplify square roots. First of all, we know that this is a square root symbol here because we don't see an index number. The square root is the inverse operation of squaring. So for example, 7 times 7 would be 7 squared. 7 times 7 is 49. If we want to undo that squaring, we would take the square root of 49 to get back 7. Now we use in math square roots so often that we've kind of gotten lazy, and when we do the inverse operation of squaring with the square root, we just kind of drop the 2 here. But normally if we look at any other roots, such as cube roots or fourth roots, fifth roots, you would always see a number here. But it is assumed that that is an invisible 2. I might as well even put the 2 there. All right, so to simplify square roots, our goal is to take the square root of any of the perfect squares found underneath that radical out and leave only the imperfect squares underneath that radical. And in order to do that, we're going to be using the product property of square roots in order to help our work here. Now, what does that property say? That property says that the square root of one quantity times the square root of another quantity equals the square root of their product. In other words, I could bring both of those quantities inside underneath that radical and multiply them together. Now first let me prove that that's true. Just take some perfect squares that you know. So if I said the square root of 4 times the square root of 9, does that equal the square root of 4 times 9? Okay, well the square root of 4, as we know, is 2. Square root of 9 is 3. And over here, simplifying, we've got the square root of 36. 2 times 3 is 6 equals, and indeed the square root of 36 is 6. So just wanted to prove that property to you. All right, taking a look over here to the right. Now how can we take this simple number 27 and simplify that? Well, we want to take out any kind of perfect squares using this property. So we know 27 is the same thing as 9 times 3. And using the reverse here, the product property of square roots, I can say that that's the square root of 9 times the square root of 3. And I know that 9 is a perfect square, so I could take that square root and say that that's 3 times the square root of 3. Now 3 inside this radical here is not a perfect square, so that's going to remain. And just by convention, we usually drop this multiplication product symbol here, and we just say that this is 3 square roots of 3. And that's how we would verbally say this number, 3 square roots of 3, which is 3 times the square root of 3. All right, great. Let's up the complexity here a little bit, and I wanted to give you a number that you couldn't readily pick out perfect squares from your memory. So I wanted to show you how to break down a number. And we can break it all the way down to prime numbers, and I'm going to do that in this case, but you don't always have to. You could just break it down until you find some perfect squares. Alright, so 432. I can see that that's definitely divisible by 2. It's an even number. And so that is 2 times 216, if I did my math correctly. And 216 is also an even number, so I could break that down. 2 times 108, which is also an even number. 2 times 54. And I'm just keep going. 2 times 27. And 27, as we just did on the previous page, is 9 times 3. And you can see here, I might as well go all the way down, even though 9 is a perfect square. Alright. So in this case, if you remember from middle school, this is called prime factorization, where we've broken down the number 432 all the way down to its factors that are all prime numbers, which is made up of 1, 2, 3, 4 2's and 3 3's. Alright, so since we are doing a square root, we're looking for pairs of numbers, because those would be squares. So here we would have one pair, 2 times 2 is 4. Another pair, 2 times 2 is 4. And we've got, of course, 3 times 3 is 9, and we already had that perfect square above it. Now the only thing that's not circled here is this number 3. That's not a perfect square, so that's going to remain underneath the radical. So let's just rewrite our number here. We have the square root of, well, we've got 4 times 4 times 9 times 3. So this is the square root of 4 times the square root of 4 times the square root of 9 times the square root of 3. And we know here that we've got 2, 2, 2. I'm just taking the square root of the perfect squares now. And that 3 is not a perfect square. So we have 4 here times 3, which is 12. And that's multiplying the square root of 3. In this case, we've completely simplified the square root of 432 down to this 12 times the square root of 3. Now, if you ever wanted to check your work, you could easily do so and make sure that you get back 432. And you could do that by going in reverse. If I were to put that 12 underneath that radical, now I would need to square instead of square rooting. So the square of 12 would be 144. So we would want to make sure that 12 squared to 3 gets back this 432. And so you could multiply those numbers out. 144 times 3. I'm getting a little cramped here on my slide, but I'm going to do it anyway. That's 12, and 12, and one more is 13. 3 times 1 is 4. Sorry, 3 times 1 is 3, plus 1 is 4. So it checks out. Just wanted to show you how you should always check your work when simplifying. Alright, now let's take a look at an expression that has variables in it. Now I use the same number, 432, just for the sake of ease here. So we know that we've got 12 here, and we've got the square root of 3 left in there. So I'm just going to use our answer from the previous page. Alright, now how do we simplify those variables? Well, they're the same thing as numbers, really. We're looking for pairs. So let's start out with the x cubed. X cubed is the same thing as x times x times x. So there's our pair right here. We've got x squared. And let's take a look at y squared. Well, that's a perfect square already, right? That's y times y, and that's our pair. And finally, we've got z to the 4th. Well, that's 4 z's multiplying each other. And that's a perfect square. We've got 2 pairs here. So let's take a look at this. We've got our 12 out front here. And we've got our square root of 3. And we've got x times x, which is x squared. That's our perfect square. But don't forget about this x here, this leftover x. And we know that y squared is a perfect square. And y, let's say z4, I'm going to break it down into its squares, z squared times z squared. Alright, so where's our perfect squares in here? Right there, right here, and right here. So let's pull those out. We've got 12, and we've got the square root of x squared times the square root of y squared times the square root of z squared. We could have even written that as z to the 4th because that's a perfect square. And what do we have left over here? We've got 3 and an x. So let's take these perfect squares. 12, square root of x squared is x, square root of y squared is y, square root of z squared is z, square root of z squared is z. And let's just simplify that last little step. Z times z is z squared. That's really what we should have done to begin with. Alright, and that would be the simplified expression of this crazy algebraic expression. And hope that helps simplifying square roots. Thanks for listening.